Okay, so let's look at a couple more examples of homogeneous equations. So this one, let's first determine that it's homogeneous or not. And we see that we've got a term here that's second degree. This is also a second degree term. And then the coefficient on the y prime is second degree as well. So it looks like we have met the requirements to be homogeneous. So the first thing we're going to do is we'll solve for y prime, right? So that gives us x squared plus 3y squared over xy, and we'll try to simplify this so that it becomes a function of either x over y or y over x. So we can break this fraction up like this, and this then is going to become x over y plus 3 y over x. And so there we go. So we are ready. We can make a substitution, letting v equal x over y and or y over x, either way, and we can we should be able to solve this using that method. All right, so let's do that. So v equals y over x, right? So what that's going to do is we'll just kind of proceed through the process. That means y equals vx. We need dy dx, right? So if we write the formula out one more time, it's the partial of v, or sorry, the partial of, so the partial of v with respect to x times dx plus the partial of v. Let's back that up a little bit. Sorry about that. Now we're doing dy dx. So dy dx, try that again. Dy dx, partial of y with respect to x times dx plus the partial of y with respect to v times dv dx. All right, again, just what we've seen before. If we do it, we get dy dx. We're just going through this again so that we can kind of get used to it. We're taking the derivative of this, partial derivative of that with respect to x gives us v times dx, which is 1, plus the partial of y with respect to v, which is x times dv dx. And there we go. And like we said, once we find dy dx, we're going to plug it in right there, as well as make our substitutions for these. So when we do that, we end up with v plus x dv dx. That's our substitution for dy dx or y prime, equals, now remember, we let v equal y over x, so this first term is 1 over v plus 3v. Right, and this is looking a lot like what we had before. This is going to yield this, x dv dx. Now let's just work without a net here, right? It's going to equal, when we solve for dv dx, it's going to equal dv dx equals 1 over x times 1 over v plus 1 over v plus 2v. And so you see we've got that thing can be written as the product of an x function and the product of a v function. And so if we combine those, combine the two v terms, we're going to end up with 1 plus 2v squared over v, right? And now we can separate the variables. So we get v over 1 plus 2v squared dv equals dx over x, separating the variables and allowing us to integrate this thing. Okay, So real similar to what we had before. Looks like we're going to use a u substitution here. So if we let u equal 1 plus 2v squared, then that means du is equal to 4v dv, or dv is going to equal du over 4v. And so our integrals are going to become, we've got our v over 1 plus 2v squared, that's our u. dv is du over 4v, and our v's disappear. Okay, so it's du over u equals integral of dx over x. So this is going to be the ln of u equals the ln of x plus, remember our little trick, we'll just call our constant ln of c, and then we back substitute in, we get ln of 1 plus 2v squared equals ln of x plus ln of c. Well, let's combine those, right? ln of c times absolute value of x, and exponentiate both sides. So we get absolute value. Well, we don't need double absolute values. 1 plus 2v squared equals c times the absolute value of x, right? And we know what v is equal to. V was equal to y over x. So we'll make that substitution because we need to get there. So we have there, we got 1 plus 2y over x squared equals c. There's that. And we can do a few things here, right? Multiply everything by an x squared. Gives us x squared plus 2y squared equals c, absolute value of x times x squared, or cx cubed, if we are dealing with just positive x's. Okay, and so there's our implicit solution. All right, we're going to run through another example here, just to show you that they're going to look real similar, but there is one little trick you kind of want to watch out for that every once in a while you've got to employ, and so we'll use this as an example. Y prime equals y, right? So I'm just going to take this, and the thing I'm looking for is, I notice that if I take this and move this over here like that, I really have no place to go, right? I can't break it up like I did in the previous example to get some y over x's or x over y's, right? It's not separable. It doesn't fit the pattern of something we can use with the integrating factor, at least in this form. But there's a little trick that you wouldn't think of, you wouldn't realize you could do it. So here's our equation, right? If I, instead of y prime, write it as dy dx, right? Then look what I can do. I can invert both sides, dx dy, right? If my answer is going to be implicit, then this doesn't matter. X being the variable or x being the function doesn't matter. So look, I've invert both sides, and now all of a sudden I can play my game, right? 2y over y, or just 2, and now that is an expression in terms of just our substitution, right? So let's run with it. Let's go. Okay, so we're going to let v equal x over y. And now we're going to solve for x, okay? X equals vy. The reason we're solving for x is because we're going to need dx dy. And so to find dx dy, it's going to be the partial of x with respect to y times dy over dy, which is 1, plus the partial of x with respect to v times dv dx. Okay? Sorry, dv dy. Like that, right? And so again, I can do that. Let's do it right here. So the dy dx is the partial with respect to y, so that's just going to be v times dy dy, which is 1, plus the partial of x with respect to v, which is y, times dv dy, and we'll leave that there. And now we're ready to make the substitution of this for this. We'll also make the substitution of this for this, right? And that will lead us to this equation right here. So dx dy equals v plus, v plus y dv dy equals, now x over y is v plus 2, right? Because 2y over y just becomes a 2. And look, all the x's are gone. And so now if we just, hopefully, remember the reason we do this substitution is so hopefully that we get a differential equation that is either separable or can be solved by an integrating factor, a linear forced order, right? So y, well, so if we solve for dv dy, we get dv dy equals 1 over y times, hey, look at that, just a 2, right? That's a dv dy. Because when I subtract v from both sides, it disappears. And so I get just 1 over y times 2. That is certainly separable, right? So it ends up becoming just simply dv equals dy 2 dy over y. And we can integrate this to get v equals 2 ln of absolute value of y plus c. And then just keep back substituting. X over y equals, well, we'll just call it ln of, look what happens when we do this. Ln of y, absolute value of y squared. We don't need the absolute value if we're going to square whatever there is there anyway. So the absolute value will drop out in this next step, and we get x equals y times ln of y squared plus c times y as our solution.